Hey everyone. So today we are looking at section 2.3, and this is, you can think of this sort of a continuation from last time. Last time we were verifying trigonometric identities, and this time we are looking at how to solve trigonometric equations. So again, some of those identities that we have looked at will come into play here. But also when we are talking about solving trigonometric equations, as they're telling us, we may actually need to use some standard algebraic techniques here. So it could be, they're calling it collecting like terms, but basically combining your like terms. It could be extracting square roots. It could also involve factoring. So basically, the first thing we're going to do here is try and isolate our trigonometric function on one side of the equation. So if you see the trigonometric functions are given on both sides, try and bring them to one side, and then we'll try to see how we can solve them. So just like an example here, they're giving us the equation 2 of sine x, or 2 times sine x equals 1. So to get the sine x by itself, we would go ahead and divide both sides by 2, and you would end up getting sine of x equals 1/2. Now at this point, you can think about, okay, for what values of x, what should our angle x be so that the function sine of x would give you a value of 1/2. So they're actually using the graph of our sine x function over here, and then this little pink dotted line that you are seeing is the line y equals 1/2. So basically they want to know where is the function going to equal 1/2, and you will see that for the interval that goes from 0 to 2 pi, which would be from here to here, we have sine of x being equal to pi over 6, and we have sine of x equal to 1/2 when x is 5 pi over 6. And so basically the idea is, if you're just looking at the interval from 0 to 2 pi, we have two different values of x where our function sine is going to equal 1/2. But again, since sine of x has a period of 2 pi, you can basically think about these as being, just going through those rotations, what we call as coterminal angles. And so that's why you can actually have infinite number of solutions here if you just add factors of 2 pi to both of these angles, where again we're using n as an integer value. So n can be 0, 1, 2, 3, 4, or it can be -1, -2, -3. So as long as those integers keep going to positive and negative infinity, you will have infinite number of solutions here. And they're actually asking us to notice what happens when n equals -1 and +1. So if n equals +1, then that's where you're getting this angle here, which is pi over 6 plus 2 pi, and you're getting this angle here, which is 5 pi over 6 plus 2 pi. And if your n value equals -1, then you are actually getting this angle on the left hand side, which is the 5 pi over 6 minus 2 pi, and pi over 6 minus 2 pi. So this little value of n, as it keeps changing between integers, you're going to get multiple different solutions. Now you can think about the graph of sine of x, but you can also use the unit circle to help you out. And remember, you guys have a copy of the unit circle that I gave you in class. So, I would say go get that out, and that will help you with a lot of these examples in here. So basically, again, we're talking about where is our sine of x function going to equal 1/2. And then, of course, you can see right here at pi over 6. And, of course, pi over 6 is the same as 30 degrees. So if you're at pi over 6, if we keep going in those rotations of 2 pi, you're going to keep coming back to the same point. So that's where you're getting infinite number of solutions from that pi over 6. And if you go in the counterclockwise, if you go in the clockwise direction, then you get negative answers. in the counterclockwise direction, you get positive answers. And of course, you can use that same rule here for the angle 5 pi over 6, which again, you know 5 pi over 6 is going to come out to be 150 degrees if you were looking at it in terms of degrees. You know, the other thing that I kind of was thinking about when I was looking through these examples, they're asking us to find the value of x when sine of x equals positive 1/2, right? So we know sine of x is positive in quadrants 1 and quadrant 2, right? So you can see these angles that we are selecting are quadrant 1 and quadrant 2 angles, and then you're going in circles with those coterminal angles, and that's how you're coming up with your solution for this. So the one thing we want to be careful about when we're going through these examples, we are going to write our answers using exact values. We are not going to be using decimal approximations. For the most part, we're going to avoid doing decimal approximations, and we're going to try and do these as exact values, okay? All right, guys, let's take a look at our first example over here. So they're giving us sine of x plus square root of 2 equals negative sine of x. And so, of course, the first thing, as I said, will be to try and get our sine of x functions on the same side. So, of course, go ahead and add the sine of x and bring it to the left-hand side. So that's what they're doing here, bringing it to the left-hand side. And then the other thing they're also going to be doing is taking this negative, square root of 2 and moving it to the other side. So it becomes negative square root of 2, and that's why this guy has become negative. So when we add sine of x with sine of x, that becomes 2 sine of x, and then of course you end up just dividing both sides by 2, and that gives you sine of x equals negative square root of 2 over 2. So again, think about it. Your sine of x function is going to be negative in which quadrants? So we looked at here, we know sine of x is positive in quadrant 1 and 2, so that itself should tell you is negative in quadrants 3 and 4. So those are where you're going to find the value of x in here. So we're looking at, okay, where is the sine of x function going to have a value of negative square root of 2 over 2? So if you just read that little paragraph here, they're saying the period of the sine function is 2 pi. We know that. So start by finding the solutions in that interval going from 0 to 2 pi, and then of course you can use the general solution. So this is going to be at the angles 5 pi over 4 and 7 pi over 4. So let me show you our unit circle here. So we are looking for where is our sine function going to have the value of negative square root of 2 over 2 and negative square root of 2 over 2. So you can see that's going to be here at angle 5 pi over 4 and angle 7 pi over 4. So like I said, use the unit circle to help you out. Once you find these specific answers in the interval from 0 to 2 pi, then you can use the idea that since pi has a period of 2 pi, we can add the multiples of 2 pi to each solution. So then you end up getting 5 pi over 4 plus 2n pi and 7 pi over 4 plus 2n pi. And then remember to always include this little statement that says n is going to be an integer. Okay? So in that same way, we have an example that we are looking at, and this guy is sine of x minus square root of 2 equals negative sine of x. So let's go ahead and take a look at this example over here. So that should be problem number 1. Okay, so the same kind of thing that you did for example 1, let's start by moving this sine of x to the left hand side. So these guys will cancel out. You can go ahead and add these two sine of x functions. So that's sine plus sine, which will be 2 sine of x. I have my minus square root of 2, and then for now we have a 0 on the right hand side. Now remember, we're trying to isolate our trigonometric functions, which means we'll go ahead and now move the square root of 2 to the other side. So these guys will cancel out. We are left behind with 2 times sine of x equals positive square root of 2. And then go ahead and divide both sides by 2. So these guys cancel out. And you are left with sine of x equals positive square root of 2 over 2, right? So if it's going to be positive square root of 2 over 2, oops, there we go. So just think of this as our unit circle. So you know, for positive sign, you are looking at quadrant 1 and quadrant 2, and this is actually come at your 45-degree angle. I don't know if you if you remember the right triangle trigonometry we had talked about. You can kind of use that also to help you out. But we are looking for where is our sine function positive square root of 2 over 2. So it's going to be at these two angles, pi over 4 and 3 pi over 4. Okay, so the way you are going to write these answers down is in the interval, because remember your sine function has a period of 2 pi, so that's why we're looking at the interval from 0 to 2 pi. Your x values are going to be pi over 4, and they are going to be 3 pi over 4. Remember, those are the two angles that I was showing you here on our unit circle. Okay, so this would be specific to that interval, but we are looking for the general solution. So in the general form, you are going to get x equals pi over 4 plus sine has a period of 2 pi, so you're going to do 2 times n pi, and then for x equals 3 pi over 4, same thing, we're going to do 2 times n pi, because remember, we are talking about coterminal angle. So this is your pi over 4, 3 pi over 4. So if you keep going in circles, with positive 2 pi, we'll keep coming back to this pi over 4. Same thing with the 3 pi over 4 if you keep going in circles. And then if you go clockwise, then again you would be getting your negative angle. So that's why we need to include this, and then remember to write n is an integer. Okay? So I hope this kind of makes sense of how we go about finding these solutions. Now let's go back to our handout. All right, let's take a look at this next example. They're talking about extracting square roots. So again, the first thing we want to do is get our tangent function by itself. So start by moving that 1 to the other side. So we go ahead and add that 1 to both sides, and then of course we'll divide everything by 3, which ends up giving you tangent squared of x equals 1/3, right? And then, let me see if I can do this here on the side. We've got tangent squared of x equals 1/3. So to get rid of that square on our tangent function, we're going to have to do square roots on both sides. And anytime you do a square root, you get one positive and one negative root, right? So your square and square root will cancel out, leaving you with tangent of x. And then here, you can separate this as square root of 1 over square root of 3. And square root of 1 is 1, and then square root of 3 will be 3. And then of course, remember, you have to then rationalize your denominator, which is how they came up with this final statement. So tangent of x equals positive and negative square root of 3 over 3. And now you have to, of course, find out what your tangent of x function would be. And so just as a note, they are talking about when you are extracting square roots, make sure you account for both the positive and negative solutions. So this is where, we brought in this little positive and negative sign in here on our square root. So that's what they're reminding you about here, okay? So again, remember that the period of the tangent function is just pi. So start by finding solutions in the interval for 0 to pi, and then we can move that to the general form. So where is your tangent function going to be square root of 3 over 3? So I'm going to take you back to the unit circle and basically think about when we are talking about the tangent function being square root of 3 over 3, that means you're actually looking at the pi over 6 angle over here, because I will take square root of 3 over 2 and divide it by the 1/2, which will end up giving you, I said that the other way around, sorry. This should be 1/2 because it's sine over cosine for tangent, so it should be 1/2 divided by square root of 3 over 2, and that will end up giving you square root of 3 over 3. And this will also happen here at this point, because remember we're looking at tangent as being positive or negative. So this one here, again, you will divide 1/2 by negative square root of 3 over 3, which will also end up giving us negative square root of 3 over 3. So it's going to be these angles, pi over 6 and 5 pi over 6. And remember, we're doing this just within the interval of 0 to pi. So that's why we only need to do the first two quadrants. You don't have to worry about quadrant 3 and quadrant 4. And then when we do the period, which is pi, you end up getting pi over 6 plus n times pi, 5 pi over 6 plus n times pi, and again, remember, n is an integer. So I hope that kind of helps you out. Okay, so let's look at our example here. This is 4 times sine squared of x minus 3 equals 0. So let's take a look at this function here. Alright, so again, we need to start by isolating our sine squared function first. So we'll start by adding 3 to both sides. So this guy will cancel out. That leaves us with 4 times sine squared of x equals 3. Divide everything by 4. Then you end up getting sine squared of x equals 3 over 4. And just like you saw in the example, now we are going to get rid of the square on the sine function. So we're going to take square roots on both sides, and this will give you a positive and a negative root. The square root and square will cancel out, giving us sine of x, and then positive, negative. I'm going to simplify this. So square root of 3 on the top, square root of 4 on the bottom. So square root of 3 will stay as it is. Square root of 4 will of course become 2. And in this case, since you got a nice integer value on the denominator of 2, we don't have to worry about rationalizing our denominators. So now we are looking at, okay, for what angles can we find the sine of x will be square root of 3 over 2 for both positive and negative values. Now remember, sine function has a period of 2 pi. So first, we are going to look for answers in the interval, which will go from 0 to 2 pi. Okay, so let's go back to our unit circle. So where can the sine function have values which will be square root of 3 over 2 and negative square root of 3 over 2? So that's going to happen right here, square root of 3 over 2 for pi over 3, square root of 3 over 2 for 2 pi over 3, And quadrant 3, you're looking at negative 3 square root of 2, which is for the angle 4 pi over 3. And this guy right here, negative square root of 3 over 2, which is for the angle 5 pi over 3. Because remember, our interval goes from 0 to 2 pi. So since our interval goes from 0 to 2 pi, that means you're looking at the entire circle. So in each quadrant, you will find one angle. So let's go ahead and write those x values down. So that will be x equals pi over 3, x equals 2 pi over 3, x equals 4 pi over 3, and the last one, we had x equals 5 pi over 3, okay? So in the general form, again, remember guys, the period of a sine function is 2 pi, so this will be 2n pi, 2 pi over 3 with again plus 2n pi, 4 pi over 3 plus 2n pi, and then for the last one, x equals 5 pi over 3 plus 2n pi, where again n is an integer. Okay, so that's kind of how we would go about finding the solution for our example 2 over here. Okay? Alright, let's come back to our handout. So we're talking about, for equations 1 and 2, we actually only had one trigonometric function, right? You were given just sine squared of x, all the others were integers. If you look at example 1, when we combined our sine x with sine x, it again just became one single trigonometric function. Now what happens if you have two or more functions in the same equation? So the first thing we're actually going to do is collect all the terms on one side, and then we are going to try separating them by factoring. So separate them by factoring, or maybe see if one of those trigonometric identities that we talked about would help us out. And what's going to happen here, sometimes you may end up with factors that may not give us any answer. You may not get any solutions to that. Because remember, you always have to think about what is the range of the function. Is this going to fall in the range of our function? Is this something that we will be able to find a solution for? Or if it is outside the range of our function, then we may not be able to find a solution for those. So kind of keep all of those things in mind when you're going through these problems, okay? So let's look at example 3 here. We've got cotangent of x times cosine squared of x equals 2 cotangent of x. So of course the first thing we're going to do is go ahead and subtract this 2 times cotangent of x and bring it to the left hand side. So that's what we're doing here, bringing it to the left hand side. And then you will see that I have a cotangent function here and a cotangent function here. So we can actually go ahead and bring it out as our greatest common factor. So from the first term, you are left behind with cosine squared of x. And from the second term, you're left behind with the 2. So we go ahead and put that in parentheses. So we're just using factoring here. And then you are going to take each factor and set it equal to 0. So take each factor, set it equal to 0, and see what kind of answers you come up with. So remember, cotangent function has a period of pi. So that's why we're looking at the interval from 0 to pi. And for cotangent function of x to equal 0, it's actually only going to happen right here at pi halves, because when you are talking about the cotangent function, and let me do that over here, cotangent function, remember, is defined as cosine of x divided by sine of x. So here, my cosine value is 0, sine value is 1, right? Here at the pi half coordinate. So that means you are taking 0 divided by 1, which gives you 0. So in this interval from 0 to pi, you will get 0 only at this angle of x equals pi halves. Okay? And then let's look at the second factor, which was cosine squared of x minus 2. Start by moving that 2 to the other side. And then, of course, we end up taking a square root on both sides of our equation. So we get plus or minus square root of 2. Now think about the cosine function. Where can you find the x value such that your cosine of x will equal positive or negative square root of 2? So let's take a look here. So this is something you should remember, that the range of the cosine function only goes from -1 to +1. And imagine the graph of the cosine function. The amplitude is only -1 to +1, right? Which makes the range of our cosine function. So the value of square root of 2 is approximately 1.414. So you can see positive or negative, these values are going to fall outside the range of our cosine function. So you will actually not be able to find any solution for this second part. So from here, you're not going to be getting any solution for your cosine function. So the only solution we got was from our cotangent function. And for the cotangent function, we got x equals pi halves. And since the period of the cotangent function is pi, your general answer is going to be pi halves plus n pi, where again, your n is an integer. Okay, so I hope this kind of made sense to you. And they're actually talking about how you can confirm by graphing this equation that we were given. So if you go ahead and graph this, then you will notice at the multiples of pi halves. So right here at positive pi halves, you've got your x-intercept, which is actually the solution to this equation. And then at positive 3 pi halves, you have your x-intercept again, which would be the solution to our equation. Or if you go on the negative side, same thing. At negative pi halves and at negative 3 pi halves, we have the solutions for our equation. Cotangent x multiplied by cosine squared x minus 2 cotangent x will give you these answers. So that's kind of what they're talking about here at the bottom of this graph. Okay? Alright guys, let's look at example 3 over here. So example 3, we've got sine squared x equals 2 sine x. Of course, the first thing we're going to do is go ahead and bring that sine 2 sine x to the left hand side. So let's start by subtracting this guy. So these will cancel out, and you will be left behind with sine squared x minus 2 times sine of x, and this will equal 0. So you will notice we have at least one sine function here and one sine function here. So we can bring that outside as our greatest common factor, but it will be only one sine function. So since I'm taking one sine outside from this first term, you will have one sine function left behind, so sine of x. From the second term, I already took the sine of x outside, so I'm just left behind with the 2 here, and this will equal 0. So just like you saw in the example, take each factor and set it equal to 0. So sine of x equals 0, or sine of x minus 2 equals 0. Okay, so this guy of course will stay as it is. We don't have to simplify it. For this guy here, we can add that 2, move it to the other side, and you will end up getting sine of x equals 2. So let's look at this first function here. Where is sine of x going to equal 0, and let's do that in the interval of 0 to 2 pi, because again sine has a period of 2 pi. So if you need help, you can look at the unit circle here again. So you will see sine of x is going to be 0 at this first origin, or not the origin, at the starting point, which is the angle 0, and then of course back here again at pi, where your sine value is 0 again, right? So at x equals 0 and x equals pi, our sine function is going to be 0 for both of those. Okay, so if we had to put this in the general form, we would go from x equals 0 plus 2n pi. Remember again, the period of a sine function is 2 pi, and this would be x equals pi plus 2n pi. So you can actually go ahead and clean this guy up. 0 plus 2n pi would be 2n pi, and we would have x equals pi plus 2n pi, where again n is an integer, right? And then let's see what's happening here excuse me, on the other side. So now we are saying, where will the sine of x function equal 2? So I don't know if you have realized this at this point or not, but there will be no solution here. And can you think about it and see why there would be no solution here? It's actually pretty similar to what you saw in the previous example. There will be no solution because 2 is going to be outside of the range of your sine function. Because sine function has the same range as the cosine function. The range of the sine function also goes from -1 to +1, and clearly 2 is going to be a number outside of this range, so that's why you have no solution from the second factor. The only solution you get is from the first factor, and that's going to be these two answers that we came up with. Okay, so I hope this kind of makes sense to you. Now I did want to make one more point, and if you don't realize this, that's okay. But what happens is, if you look at the answers that we had here, x equals 2n pi and x equals pi plus 2n pi. So, your n are just going to be integers. So n can be 0, 1, 2, 3, or they can also be negative numbers. So if you put 0 for n, of course you're going to end up getting, if n was 0, then for this first one, let's call this x1 and x2. So for x1, you would end up getting 2 times 0 times pi, which would end up giving you 0. For x2, you would have pi plus 2 times 0 times pi, which would end up giving you pi as the answer. If n was 1, for our variable x1, you would end up getting 2 times 1 times pi, which would be 2 pi. For x2, you would end up getting pi plus 2 times 1 times pi, which would actually end up becoming pi plus 2 pi, or that actually comes out to be 3 pi. So if you kept going, you would actually see, so if you tried this for n equals 2, you can kind of see what those answers would come out to be. So these answers actually go from 0 to pi, 2 pi, 3 pi, and you would have, if you did these calculations here, you would have 4 pi for x1, and you would have 5 pi for x2. And then if you switched to negative n values, you would end up getting x1 as, let me make sure I get this correct, because this guy would then end up being negative 2 pi, and x2 would end up being negative 2 pi plus pi, so he would end up being negative pi. So now you would start going into the opposite direction, so you would have negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So these guys are actually increasing in the increments of pi, so you could potentially rewrite your x value as just being x equals n times pi, where n is an integer. But like I said, if you do not see this and you don't write it as n pi and you just leave it as 2n pi plus and the other one pi plus 2n pi, I will be okay with that. But if you see that it can consolidate down to x equals n pi, then that's great, and if not, then just leave it what you had. So just something I wanted to point out to you guys. Okay, so this was example 3. Okay, now let's talk about equations of the quadratic type. So remember, this is our quadratic equation, ax squared plus bx plus c equals 0. So you can solve quadratic equations either by using factoring, or if factoring doesn't work, you can still always use the quadratic formula. So let me just go ahead and write the quadratic formula for you here. That's x equals negative b plus or minus square root of b squared minus 4ac, and then the whole thing divided by 2a. So these are the a, b, and c values we are using from our quadratic function. And again, if you just need to review some of this information, you can go to section P2 in your textbook to look at the review for this. Alright, so let's take a look at what these quadratic type of equations will end up looking like. So here you've got 2 sine squared of x minus sine of x minus 1 equals 0. So if you think of your sine of x as, let's say, being your x variable in a way, then you've basically got 2 times x squared minus x minus 1. So that's kind of what they're talking about here as our quadratic type of these functions. Same thing here, you can think of this secant squared, secant of x as being your x variable. So that's basically your x squared minus 3x minus 2. So that's kind of the format they are talking about here, and I'll show you more as we work through these examples to make sure you know what I'm talking about here. So let's take a look at example 4 over here. So you are given 2 sine squared of x minus sine of x minus 1 equals 0, and they're specifically asking us to find the solutions in this interval from 0 to 2 pi. So they are not asking you for the general form of the equation. When if they would have just said find all the solutions and they did not specifically say in the interval 0 to 2 pi, then we wouldn't worry about it and we would go ahead and do our general solution. So since this one is asking for specifically in the interval, you will not have to worry about adding the 2n pi like we did with the previous examples. So let's take a look at this guy here. So you're given 2 of sine squared x minus sine of x minus 1 equals 0. So if you just think about the sine of x function being our variable, and you know what, let's call it variable, I don't know, z. So you can actually rewrite this original equation as 2 times z squared minus z minus 1. So think of this sort of like you are doing a substitution, and then you can go ahead and factor this quadratic equation. So you will have 2z for the first one z for the second one, your negative 1 will break down into negative and positive 1. So you will have 2z minus 1 and z plus 1, but will this give us negative z in the middle? No, it will not. So I will actually need to switch my signs over here, 2z plus 1 and z minus 1. So yeah, that will give me negative z in the middle. And then basically go ahead and replace that z again with sine x. So you will get 2 sine x plus 1 and then sine of x minus 1, and then set each factor equal to 0. So that's kind of the idea of looking at these equations as being of the type of quadratic equations, and then like I said, using factoring or the quadratic formula to solve these guys. Alright, so once you have your factors, take each factor, set it equal to 0. So we've got 2x plus 1 equal to 0 and sine of x minus 1 equal to 0. Just like you did in the first couple examples, get that sine of x function by itself, move everything else to the other side, and then using your unit circle, find out where your x values for the angles will be, so that you get sine of x equals negative 1/2. And then same thing, get the sine function by itself, move the 1 to the other side, and using your unit circle, come up with x equals pi halves. Now remember, they said only to find the intervals from 0 to 2 pi. So you will notice we are not adding the 2n plus 2n pi to any of these answers. We're leaving them exactly as what we found them to be. And then this second part here is just showing you how you could also use the graph to help you come up with your values for the x-intercept, where your graph would be crossing the x-axis at. So that would be this point here, and this point here that they're looking at. Okay, but again, we're not going to worry about graphical solutions for us. Alright guys, so let's see how we can translate this example into our problem here. So we are given 2 sine squared of x minus 3 sine of x plus 1 equals 0. And again, we're only doing this in an interval from 0 to 2 pi. So let's go ahead and take a look at this example here. So again, if you imagine your sine of x function as being, again, I'll just use the same variable z, then you can go ahead and write this as 2z squared minus 3z plus 1 equal to 0. So basically I'm just replacing the sine squared of x with z squared and the sine of x with z. And then here, working on the side as scratch work, then we can try and see, okay, how do I factor these two, how do I find these two factors from our 2z squared minus 3z plus 1. So basically we're looking for 2z squared, which will break down into 2z and z here. Then your constant term 1 will break down into 1 and 1, right? Now you will notice how we have a minus sign in the middle term for the 3z, but we have a plus sign for the constant term, the plus 1. So since I have a minus in the middle and a plus on my constant term, that tells me both my factors are actually going to have a negative sign in there. Okay? And now all you have to do is bring this over to the left-hand side. So this will factor into, now instead of z, we're going to write it as 2 sine of x minus 1. For the second factor, again, instead of z, we are going to write it as sine of x minus 1 equals 0. And then once you have your two factors, you will go ahead, take each one of your factors and set it equal to 0, and then see what kind of x values you come up with. So let's take a look at that. starting with my first one, 2 sine of x minus 1 equal to 0, or sine of x minus 1 equal to 0. And remember, this was just scratch work on the side. I'm going to go ahead and start by adding this 1 to both sides. That gives us 2 sine of x equals 1, and then divide everything by 2, which will give you sine of x equals 1/2. Or on this side, we'll go ahead and add this 1, which will end up giving us sine of x equals 1. Okay, so now for each one of these, we need to come up with our answers. So again, go back, look at your unit circle, and see for sine of x equals 1/2, what x values will work. So again, remember guys, we are doing specifically for the interval 0 to 2 pi here, and same thing for the other side. So we basically want to know where the sine function is going to be 1/2 and where the sine function is going to be 1. So let's go to our unit circle. Sine function is 1/2 right here at pi over 6, at 5 pi over 6, and that was a positive 1/2, right? So it's only going to be those two numbers. And then where was our sine function equal to 1? And it's equal to 1 at pi halves. So those are going to be the three angles that we will actually be looking at. Okay, so let's come back here for pi halves. Your x values were going to be pi over 6 and 5 pi over 6. For the sine of x equals 1 function, your x value was of course going to be at the 90-degree angle, or basically at pi halves. So again, remember, they are not asking us for the general form. They are asking us for the answers only in the interval from 0 to 2 pi, and we know sine function is going to be positive in quadrant 1 and quadrant 2. So that's why we're only using these three angles. We're not looking at quadrant 3 or quadrant 4. So your solutions for this example are going to be x equals pi halves, x equals 5 pi over, oh, hold on a second. Yeah, I guess that'll work. And x equals, oh, I just realized what I did. This guy should be pi over 6. That's why I was wondering, why do I have pi over 2 on this side? So this here should be pi over 6 and 5 pi over 6. So those are the two answers. And then from the other side, we have pi over 2. So together, these three make up the solution for this example. Okay, so I hope this kind of helps you see how we are solving these trigonometric equations of the quadratic type. Okay. Alrighty. Now let's see, we have a trigonometric function here, which is 2 sine squared of x plus 3 cosine of x minus 3 equals 0. So the first thing you should notice is this is actually both the sine x and the cosine x function. So you of course cannot work when they are two different functions, sine and cosine. So we need to actually convert them into being one single function here. So in this case, what we're actually going to do, since my middle term is cosine, I'm going to take my sine square function and rewrite it as a cosine function also. And we're actually using this Pythagorean identity here to make that substitution happen. So we're going to replace our sine squared of x with 1 minus cosine square. So we're taking this function here and replacing it with this here, 1 minus cosine squared of x. And then of course you'll go ahead and distribute that 2 inside the parentheses. And then you're getting 2 times cosine squared of x here. And then 2 times 1 is being added with this minus 3 here. So I'm trying to see why he became a positive 1. Because it's minus 3, you're adding 2 to it. Is there a typo on this? Okay, I will need to go back and see what's happening here. Oh, I just figured it out. Okay, never mind. Because when you are multiplying 2 times 1, you're going to get 2. And then when you multiply 2 times with negative cosine squared of x, you are actually getting a negative 2. So that's why we're going to multiply both sides of our equation by negative 1. And when we multiply by negative 1, it's actually going to change the signs on all of this. So your negative cosine squared here becomes positive 2 cosine squared. This positive 3 cosine of x became negative 3 cosine of x, and that's why this negative 3 here, when you added it with the 2 times 1, ends up becoming positive 1 over here. So if you want to just get a feel for it, I would say go ahead and simplify this on your own and see how we go from this step here to this step here. Okay? I made a big mess there. There we go. And then of course once you get down to this last part here, then you can go ahead and factor it to 2 cosine x minus 1 and cosine of x minus 1. So take each factor, set it equal to 0, and find your x values. And looks like the solutions for these guys are coming out to be x equals 0, x equals pi over 3, and x equals 5 pi over 3. But you will notice in the original equation, they didn't ask us to stick to a specific interval. So that means you would be looking for a general solution here. And that's what these guys come out to be. So that's why you're adding 2n pi to each of your solutions individually. Okay? Alright, so let's see how we can do this for our example. So you will notice in our example also, we are given 2 different trig functions. We have secant and tangent. So we're going to need to convert this into one function, right? So let's take a look at this guy. This is number 5. We're given 3 secant squared of x minus 2 tangent squared of x minus 4. So the substitution we're actually going to be doing is for the secant function, and the identity we are going to be using is a Pythagorean identity again, which is secant squared of x is equal to 1 plus tangent squared of x, and we're going to make that substitution happen right here. So let's rewrite this guy. Instead of secant squared of x, I'm going to replace it with 1 plus tangent squared of x, so that we have everything in terms of tangent now. And then bring everything else down, so that's minus 2 tangent squared of x minus 4 equal to 0. So the first thing we're going to do is go ahead and distribute this 3 inside the parentheses. 3 times 1 is 3. 3 times tangent squared of x minus 2 times tangent squared of x minus 4 equals 0. So you can combine positive 3 with negative 4. And you can also combine these two terms, right? Positive 3 tangent squared minus 2 tangent squared. So 3 tangent minus 2 tangent will be obviously just 1, right? So that will be 1 tangent squared of x. And then with the constant terms, the 3 minus 4 will of course end up giving you negative 1. So you end up getting tangent squared of x minus 1 equal to 0. And now we're going to try and isolate the tangent function. So we will start by adding 1 to both sides. These guys cancel out. You're left with tangent squared of x equals 1. And then basically we can get rid of that square on the tangent function by using square root. So that's positive and negative. Square root and square cancel each other out. And let's see, we've got tangent of x equals plus or minus 1. Now remember the period for the tangent function is only pi. So for now we are going to be looking for answers in the interval going from 0 to pi. Okay? So 0 to pi, and we want to see where the tangent function is going to equal positive or negative 1. So I'm actually going to go back to our unit circle here. So remember, for tangent to be positive or negative 1, that means your sine and cosine values have to be the exact same number, but the signs can be different. So that's going to happen right here at pi over 4, because you can see I have square root of 2 over 2 for both sine and cosine. And right here on the quadrant 2 side, which is negative square root of 2 over 2 for cosine, and then square root of 2 over 2 for sine. And remember, you're only looking at the interval from 0 to pi, so that's going to be quadrants 1 and 2. So those are the two angles you are looking at, pi over 4 and 3 pi over 4. So specifically to those intervals, we have pi over 4 and 3 pi over 4, but this is of course looking for the answer in the general form. So in the general form, you're going to have x equals pi over 4, and then again remember the period of a tangent function is pi, so you are adding n pi to both of these angles. And again remember, n is an integer. So that's going to be your answer for, what was this, example 5. Okay? Alrighty. Now what happens here is, sometimes we may, instead of using square roots, we may actually have to use square on each side of our equation, so that we could actually make our equation look like a quadratic type of an equation, and then use factoring or the quadratic formula to help us solve this. But what happens, and I don't know if you guys remember this from college algebra or not, we had talked about this in college algebra also. So what happens is, if you actually take square on each side of your equation, there's a very good chance you could be getting an extraneous solution. Extraneous solution basically means you're getting an extra solution which will not satisfy the original equation that you started out with. So you are going to need to check your solutions and see which ones are the valid solutions and which ones are going to be extraneous. If anything is extraneous, discard it, and then of course anything that's valid, you would keep it. But remember, you're always checking in the original equation itself. So to demonstrate that, we are looking at example 6 over here. We are given cosine of x plus 1 equals sine of x, and they're asking us to solve it specifically in the interval from 0 to 2 pi. So if you just think about it this way, there are no squares on our cosine or sine function, so we cannot bring in any identity to substitute. So really at this point, we don't have much that we can do. And that's the reason why we're going to need to bring in the square on each side of our equation. So the first thing you're going to do is take each side of your equation and square it. So for the left-hand side, you will need to FOIL it, which will give you this expression here, cosine squared of x. plus 2 cosine of x plus 1. And then, of course, the right-hand side will just become sine squared of x. Now that you have sine squared of x on the right-hand side, you can bring your Pythagorean identity and rewrite sine squared of x as 1 minus cosine squared, because, again, we don't want cosine on one side and sine on the other side. So we are going to use this Pythagorean identity to rewrite the entire equation with a cosine function, and then, of course, go ahead and move this right-hand side to the left-hand side. So you end up subtracting this one, adding the cosine squared of x. So that's where this minus 1 is coming from, and this additional cosine squared of x is coming from by moving the left side, right-hand side terms to the left-hand side. So combine like terms, so these guys add up to 2 cosine squared. This guy is staying the same, and then, of course, positive 1 and negative 1 cancel each other out. And then here, since both my functions have a 2 and a cosine in common, we are taking that outside as a greatest common factor, and that leaves you behind with cosine of x, and 1 is a placeholder for the second term. Okay? Take each factor, set it equal to 0, and then try to find out what your answers would be for cosine of x equal to 0, which will give you x equals pi halves and 3 pi halves. For the second factor, you get cosine of x equals negative 1, and for that, your x value will be pi. Okay? Now, you're getting 3 different answers from here. Now, remember, we had to square our original equation to see what we could do about solving this. So that means now we have to check for those extra solutions, check for the extraneous solution. So for each one of these, we are going to do a check here. So we're starting out with pi halves, and I'll come back to this remark in a minute here. So we're going to check for pi over 2. Remember, put it into the original equation. If you get the same number on both sides, we can say the solution checks, and we're going to keep this answer. Now, we're going to check for the 3 pi halves, which was our second solution. So again, in the original equation, but I'm getting positive 1 here, and I'm getting negative 1 here. So the solution does not check, which means I cannot use x equals 3 pi halves as part of my answer. And then the last number we came up with was x equals pi. So let's check for x equals pi in the original equation. Negative 1 plus 1 gives you 0, and you're getting 0 equals 0. So your solution checks, which means I can use x equals pi also. So those would be our 2 solutions out of the 3 that we came up with, because this 3 pi over 2 did not work for us. So that's why these 2 guys are going to be your solutions. And remember, they told us to find our solution specifically to the interval 0 to 2 pi. And that's why we're not adding 2n plus pi to our answers, because we don't want the general form. We just want the specific answers to those intervals, okay? So what this little remark here is talking about is basically how we use the square on both sides of our functions, and you ended up getting sine squared on this side, and then we know we can use the Pythagorean identity to get the 1 minus cosine squared of x right here that we did. So that's what they are talking about, that in trigonometry we know that the squares have a relationship with sine and cosine, and that same is true for squares of secant and tangent, and then of course for the squares of cosecant and cotangent, because they form pairs with each other. So they're just kind of reminding us about the Pythagorean identity for those 6 different functions and what that relationship looks like. So depending on what example we have, we might need to use one of those Pythagorean identities. All right, guys. So let's look at example 6 for us. And you will notice it's very similar to the previous example. We are given sine of x plus 1 equals cosine of x. And again, we're doing this just for the specific interval 0 to 2 pi. So remember, you do not need the general form for the solution in this case. So let's go to our notes here and see how we can solve this. So it's going to be very, very similar to what we did. And you know, if it helps, put a little note for yourself that we need to check for extraneous solutions. Okay, so we don't forget about it. So this is where we're going to start by taking both sides of our equation and square those, right? So square both sides of our equation. Now remember, on the left hand side we're going to need to do a FOIL here. So let me show you what this will be. We are taking sine of x plus 1 to the second power, and we need to do a FOIL with that. Oops. Okay, so that means we're going to do sine of x times sine of x, which will end up giving us sine squared of x. Then you're going to do sine of x times 1, so that's sine of x. Then of course we're going to do 1 times sine of x, which will also give you a sine of x. And then the last one will be 1 times 1, and of course 1 times 1 is 1. So here, those two middle terms, you will be able to combine them together, right? So sine squared of x plus 2 sine of x plus 1. And once you have that answer, then we can come back to our original problem. So I'm going to replace my left-hand side with sine squared of x plus 2 times sine of x plus 1. And then of course on the right-hand side we have cosine squared of x. And again, this was just scratch work here. So just like you saw in the previous example, we're going to need to change this with a trig identity. So I'm actually going to replace my cosine squared of x with 1 minus sine squared of x. Okay, so let me go ahead and write this left-hand side first. And then replacing that cosine squared of x with 1 minus sine squared of x, because again we want all our functions to be in the sine terms, right? We don't want sine and cosine both. So we make this identity substitution help us out. And then of course now you want to move everything to the left hand side. So I'm going to subtract my 1, and then I'm going to add my sine squared of x. So I'm basically moving everything from the right hand side to the left hand side. So when you add these guys together, sine squared plus sine squared will become 2 sine squared of x. My middle term is 2 sine of x. And then here, positive 1 and negative 1 will also cancel out. So you're basically now just left with 2 sine squared of x plus 2 sine of x equals 0. And then each one of these terms has at least one sine of x that's common, and they also have this number 2, which is common between both our terms. So we're going to take that number 2 and one of the sine x functions outside as our greatest common factor. So from this first term, my 2 is gone, I've got it outside, and I've got one of these sine x terms which has come outside. So I only have one sine of x left behind, plus sine in the middle. Then from my second term, again, I've taken this 2 outside already, and this sine of x has also been taken outside. So since I have nothing else remaining, I'll put 1 as a placeholder, and then again you have 0 on the other side. So this is how we do factoring here. And then remember, at this point, we take each of our factors and set it equal to 0. So you should have 2 sine x equal to 0, or sine of x plus 1 equal to 0. On the left hand side here, we're going to divide both sides by 2. 2 and 2 cancel out. giving you sine of x equals 0 for this first part. And then here, we're going to subtract 1 on both sides. This will cancel out, giving us sine of x equals -1. So once you have this, then in the interval, and remember we are going from 0 to 2 pi. Same thing on this side. So again, if it helps, go look at the unit circle. So you're looking for sine of x equals 0 and sine of x equals -1. So sine of x is 0 right here at the starting point, 0. And sine of x is 0 here at the angle pi. And sine of x is going to be +1 at the 90-degree angle. So that's pi halves. And I think that's all we have, right? Oh, sorry, that was a -1. My mistake. So you're not actually looking at pi halves, you're actually looking at -1. So that's going to be 3 pi halves. So at the 270-degree angle. So we will have angle 0, angle pi, and then angle 3 pi over 2 as our possible solution. So for sine of x equals 0, your x values will be 0 and x equals pi. For sine of x equals -1, your x value is going to be 3 pi over 2. But remember, guys, we are not done at this point. So we've got these three x values as our solutions. But remember that little note we put for ourselves? We need to check for extraneous solutions. So we still need to do this part right here. So let's take each one of these, and remember you're going to put this in your original equation, which was sine of x plus 1 equals cosine of x. So let's do our checking next. Our original function is sine of x plus 1, there we go, equals cosine of x. So let's start with x equals 0. That would be sine of 0 plus 1 equals cosine of 0. So remember, sine of 0 is going to be 0. Nope, sorry, I think I did that wrong. No, I was on the right track. I don't know why I confused myself and I was thinking 1, but sine of 0 is 0. So this will be 0. I have plus 1 here. And then cosine of 0 is 1. So we end up getting 1 equals 1, which is a true statement. So that means this guy is good to go. Okay, we can use him. Then my next one was x equals pi. Alright, so let's check for this guy. So that will be sine of pi plus 1 equals cosine of pi. So again, we know sine of pi is at the 180-degree angle. So in this case, your sine of pi will be 0 plus 1. But now, cosine of pi is actually going to be -1. So you are getting +1 equals -1. And we know that's not true. We are getting a false statement here, which means we cannot use x equals pi as part of our solution set. And then the last one we got to check is for 3 pi over 2. So this would be sine of 3 pi over 2 plus 1 equals cosine of 3 pi over 2. So remember, this is that 270-degree angle. So in this case, sine of 3 pi over 2 is -1. Then we've got our plus 1 and that equals cosine of 3 pi over 2, which is of course going to be 0. So negative 1 plus 1 on the left-hand side will also become 0, and you end up getting 0 equals 0, which is a true statement. So that tells us that x equals 3 pi over 2 is okay to use. Okay. So again, remember, no general form because we're only doing this from the interval 0 to 2 pi. So our answers for this equation are going to be x equals 0. I want to make sure I can see those. There we go. And x equals 3 pi over 2, which is going to be in the interval from 0 to 2 pi. And so these two are the only answers we can keep. Okay, so I can kind of see how this works out. And remember, this is happening because originally we were given sine of x plus 1 equals cosine of x. And since we ended up taking a square on both sides of our equation, that's what created this extra solution of x equals pi. And since it did not satisfy our original equation, we kicked him out. Okay? Alrighty, let's look at this example over here. Now this is talking about functions that are involving multiple angles. So when we're talking about multiple angles, you can see right here in your example, that means you have cosine of 3t. So they're just not giving you cosine of x or cosine of theta. They're actually now multiplying it with a constant term. So you have, instead of just giving you cosine of t, they are now giving you cosine of 3t. So basically and that's what we're calling in terms of multiple angles. So since we have equations in this form, what we're actually going to do is first solve and pretend like that was just cosine of x. So you're going to first solve your function, which has this ku, where k is your constant. So the first thing you're actually going to do is solve your equation with that ku term, keeping it as it is. And then once you find the answer for that, then you actually end up dividing your result by that constant value of k. So it will make more sense when we look through this example over here. So we've got 2 times cosine of 3t minus 1 equals 0. So again, we want to isolate our trigonometric function first. So that means we want to get cosine of 3t by itself. So start by moving that 1 to the other side by adding. Then we divide by 2 and you end up getting cosine of 3t equals 1/2. So just think of this as being one single angle right now. So you're basically saying, where is the cosine value going to equal 1/2? So again, looking at our interval from 0 to 2 pi, you can again go to your unit circle and look for the angles where your cosine function is now positive 1/2. So that's going to happen right here at the 60-degree angle, which is pi over 3. And it's going to happen here at this 300-degree angle, which is going to be 5 pi over 3. So those would be, the two angles, so pi over 3 and 5 pi over 3. And once you get that, then what you're going to do is take your 3t, set it equal to your pi over 3 plus 2n pi, and 3t equals 5 pi over 3 plus 2n pi, and then you're actually going to end up dividing both of these by 3, which means you are dividing this entire right-hand side by 3, which is actually, if you're dividing by 3, I think it would be better to write it this way. You can think about it as being multiplied by 1/3. So dividing by 3, or think about it as being multiplied by 1/3. So if you look at your general solutions here, since we're multiplying by 1/3, your pi over 3 will now become pi over 9. And then the 2n pi will now become 2n pi over 3. And for the second part where you had 5 pi over 3, that will now become 5 pi over 9. And then the 2n pi will now become 2n pi over 3. So that's actually how you basically have that one extra step where once you find your angles, then just divide by that k constant term, which in this case was 3. So divide your general form of the solution by that 3, and you will get your answer for the original equation that you started out with. Okay? So that's the same kind of thing we're doing obviously in number 7 here. So we are given 2 times sine of 2t minus square root of 3 equals 0. So let's see how we can go about solving this guy. So start by isolating the sine of 2t, which means the first thing we're going to do is add square root of 3 on both sides, which will leave us behind with 2 times sine of 2t equals positive square root of 3. And then of course divide everything by 2. So now we are left with sine of 2t equals square root of 3 halves. So in the interval, and again sine has a period of 2 pi, so you would be going from 0 to 2 pi. We are looking at where is the sine function going to be square root of 3 over 2, and that's a positive square root of 3 over 2. So sine function is square root of 3 over 2. Again, that's at the 60-degree angle, so that's your pi over 3. And it's also going to be the 120-degree angle, which is going to be 2 pi over 3. And I think those are the only two angles where we have a positive square root of 3 over 2. So here in this case, now remember this is still a multiple angle of 2t. So you will say 2t equals, and what were those angles I told you? Pi over 3. And again you would have 2t equals 2 pi over 3, right? Okay, so this was in the specific interval from 0 to 2 pi, but in the general form, we would have to add to n pi, right? Same thing for that other angle, 2 pi over 3, and we would be adding 2n pi. And then to get t by itself, and I'm going to do this in a different color so you can kind of see, we're going to divide all of these basically by 2. Okay, so that means you will actually end up getting, so this 2 and 2 will cancel out, and you will end up getting t equals, and remember dividing by 2 is the same thing as multiplying by 1/2. So I'm going to do this side first and then come back to the other side. You will end up getting t equals, so you're going to be multiplying the 2 and the 3 on the bottom, and this will actually end up becoming pi over 6. And then on this side, this 2 on the bottom will actually end up canceling this 2 from the 2 and pi and leaving you behind with just n pi. Okay, so alright, let me recap that before I go to the other side. So we're taking this 2 here and dividing it on both sides. So from 2t divided by 2, your 2 cancels out, leaving us behind with just t on the left hand side. And then on the right hand side, when you're dividing by 2, like I said, just think about multiplying by 1/2. So that's 1/2 times pi over 3, which will end up becoming pi over 6, because 1 times pi is pi, 2 times 3 is 6, which gives us that new denominator. And then when you multiply 2 and pi with 1/2, the 2 and the 2 cancel out, because remember, you're still dividing by 2. So even if you think of this as being divided by 2, the 2 and 2 cancel out, leaving you behind with n pi. And then same kind of thing is going to happen here for our second angle. So 2t divided by 2, so the 2's cancel out, leaving us behind with just the t. And then we are doing 1/2 multiplied with 2 pi over 3. And then 2n pi is also being multiplied by 1/2 or divided by 2. So on this first part, this 1/2, the 2 on the bottom and 2 on the top cancel out. And same thing on the second side, this 2n pi, the 2 and the 2 on the bottom will cancel out, leaving us behind with t equals pi over 3 plus n pi. Okay, so pi over 6 plus n pi and pi over 3 plus n pi are going to be our final solutions for this example. So I hope you can kind of see how those multiple angle problems come out to be. So again, just start by solving as though you're not worried about the 2t for now. You have sine of this angle, whatever it is, equal to square root of 3 over 2. Using our unit circle, we came up with the answers of pi over 3 and 2 pi over 3. And once you have those answers, put it in the general form by adding the 2n pi, and then divide everything by 2. When you clean it up, these are the two answers that we come up with. So I hope this helps you guys out. Okay? Alrighty. So just another example to look at these multiple angle equations. So instead of having something like 2t or 3t, you are now given x over 2 as your multiple angle. So this example, we have 3 times tangent of x over 2 plus 3 equals 0. So again, start by moving the 3 to the other side, and then we'll divide everything by 3, which will end up leaving us behind with tangent of x over 2 equals -1. Now again, you can use the unit circle to see where your tangent value is going to be -1. And of course, as you can see, that's going to happen here at the 135-degree angle for 3 pi over 4. And since tangent only has a period of pi, you're only looking at the interval 0 to pi, which means the first two quadrants. So it looks like it's going to be at 3 pi over 4, and that's exactly what we have here. And then, of course, doing the general solution, we go ahead and add the n pi. Now, what's going to happen here actually is, since we have x divided by 2, to get rid of that 2, you are going to end up multiplying both sides by 2. So when you distribute that 2, you end up getting 3 pi over 4 multiplied by 2 will become 3 pi over 2. And then n pi times 2 will, of course, end up becoming 2n pi. And that's going to be the solution for example 8. Okay? So as you can imagine, we're going to have a similar experience with our problem number 8 here. We are given 2 times tangent of x over 2 minus 2. So let's go ahead and take a look at how we can solve this guy. So isolate the tangent function first. Sorry about that. Let's do this. There we go. Add 2 to both sides. This guy here will cancel out. You are left with tangent of x over 2, and then of course we have that 2 in the front. So we want to go ahead and divide both sides by 2 to get our tangent function by itself. These guys cancel out, leaving us with tangent of x over 2, and of course your right hand side will now just become positive 1. So like I told you before, tangent has a period of pi, so you are looking at the interval from 0 to pi, and you're trying to see this time where your tangent function is going to be positive 1. So for it to be positive 1, our sine and cosine functions both also have to be positive and have the same value. So that, guys, is going to happen right here at the 45-degree angle for pi over 4, and that's going to be the only angle between our 0 to pi interval. So that means our angle x over 2 has to be pi over 4, and this is of course in the interval. So in the general form, this answer will now become x over 2 equals pi over 4, and then again remember, tangent has a period of pi, so you will be adding n times pi. And then to get our x by itself, we're going to end up multiplying both sides of this equation by 2. So your 2 and 2 will cancel out, leaving us with x. And then you are basically doing 2 times pi over 4 plus 2 times n pi, right? Because this 2 gets multiplied with both of these terms. So 2 will go into 4 twice, and this will end up giving you pi halves for the first part, and then 2 times n pi will just end up becoming 2n pi. And so this guy, as your final answer, comes out to be x equals pi halves plus 2n pi. This is our solution for this equation. So it's not too bad once you actually figure out how those multiple angles work out. But yeah, when you first look at them, it kind of seems like, ooh, I don't know how I'm going to solve those. So kind of look through those examples, and then of course look through your homework and let me know if you have any questions regarding any of these, okay? Alright guys, we're getting close to the end of this section, just a couple more examples here. So this one is talking about how we can use inverse functions to help us solve some of these equations. So we are given secant squared of x minus 2 times tangent of x equals 4. So we're bringing the 4 to the left hand side. So the first thing we're doing is subtracting this 4 and bringing it to the left. And the other thing we are doing, we're actually using the trigonometric identity here for secant squared and replacing it with 1 plus tangent squared. So the secant squared is getting replaced and the 4 is moving to the left hand side. Just combining your like terms and simplifying that left hand side, you end up getting tangent squared of x minus 2x minus 3 equals 0. And they are actually using the idea that this is a quadratic type of an equation, and so they're using factoring to simplify the left hand side. So you're getting tangent of x minus 3, set that equal to 0, and then tangent of x plus 1 and set that equal to 0. So let me show you here what's happening. So we take tangent of x minus 3, set it equal to 0, then of course you move that 3 to the other side and you end up getting x equals 3. And this is where they're actually bringing the idea of using arctangent or the inverse function and coming up with x equals arctangent of 3. And in that same way, they are taking the second factor, which was tangent of x plus 1, setting that equal to 0. Then again moving that 1 to the other side, which becomes negative 1. And then again using our arctangent function to write it as x equals arctangent of negative 1. So that is where this x equals arctangent of 3 is coming from, and x equals arctangent of negative 1 is coming from. So if you look at this little sentence over here, they're saying by setting each factor equal to 0, you obtain the two solutions in the interval of negative pi halves to pi halves. And the reason we are going from negative pi halves to pi halves is because the range of the arctangent function or the inverse tangent function is from negative pi halves to pi halves. And so by using the inverse functions, we're changing our interval here and going from negative pi halves to positive pi halves. And in that interval, you have to think about, okay, where is arctangent of 3 going to give you as an answer, or what x value you come up with, and for x equals arctangent of -1, what does that value come up to? So if you actually look at your unit circle, you can also kind of help you come up with those numbers. So it's actually coming from, remember your interval goes from negative pi halves to positive pi halves, which means you're actually looking at quadrants 1 and 4 to find your answers. And since we are looking at angle of negative pi halves, you're actually going partially in the clockwise direction and partially in the counterclockwise direction. So right here at this angle of 315 degrees, when I divide these two values, I get -1, and so that's why we're using this angle of 7 pi over 4, which in clockwise direction, this angle will now become negative pi over 4. So that's actually where they are getting this answer of negative pi over 4 for the arctangent function. Okay, and arctangent of 3, if you actually try to use your calculator for that, you will notice that arctangent of 3 actually ends up giving you, and I wrote this down so I wouldn't forget. There we go. So it actually comes out to be approximately 71.6 degrees or 1.2 radians. So right here for this guy, 71.6 degrees or 1.2 radians. So of course that's a number you're not going to find on your unit circle, right? So that's why for x equals arctangent of 3, we didn't simplify it any further, because the angle is such an odd number, but or not a good number. But for x equals arctangent of -1, since we were able to simplify it, we gave you negative pi over 4. So again, using the idea that tangent function has a period of pi, you can then go ahead and add n pi to both of these answers, and they're telling you you can kind of use the calculator to approximate the answer for arctangent of 3. Okay, and again, remember guys, n is going to be an integer. Okay, all right, so let's take a look at how we can solve our example 9, problem number 9 here. So let's take a look at it. So we are given 4 tangent squared of x plus 5 tangent of x minus 6 equals 0. So the first thing we're going to need is see if we can factor our left-hand side here. So let me do this. We're going to try and rewrite these guys. So let's say again we use tangent of x equal z. So that will end up giving us 4z squared plus 5z minus 6 equals 0. So we're basically replacing tangent squared of x with z squared and tangent of x with z. Okay? If you think factoring is going to be too hard for you, then remember you can use the quadratic formula for this also. So you don't always have to use factoring. I just kind of always end up going with factoring because I find factoring to be easier, but you're definitely welcome to use the quadratic formula here if you like. So this guy, what's going to happen here, and let me show you. Basically what's going to happen is we're going to multiply this leading coefficient 4 with this constant term -6. And I'm going to do this a little bit here on the bottom. So 4 times -6 ends up giving us -24, and then we are trying to find factors of -24, which will add up to give us this middle term. of positive 5. So factors of 24, of course, you've got your 12 times 2, 4 times, what's that, 6, 8 times 3, 1 times 24, of course, is there, but those numbers are too far apart, so they don't work. So I'm thinking 8 and 3 can work, because if I subtract them, I get a total of 5. And so since it's a positive 5, that means 8 has to be positive and 3 has to be negative. So using those numbers, I am going to split our middle term. So this will become positive 8z. This will be negative 3z minus 6 equals 0. So we're basically keeping the first and the last terms the same. We're using these numbers 8 and negative 3 to split open our middle term. So we're actually splitting up our middle term by using that positive 8 and negative 3. Now, I'm actually going to get rid of these lines that I just drew. Okay, so we're basically splitting up this 5z into 8z and negative 3z. And now to get our factors, I'm going to group the first two terms and I'm going to group the last two terms and see what's common between them. So between 4z squared and 8z, 4z is going to be common, which will leave us behind with z plus 2 on this side, keeping that same minus sign here. Between 3z and 6, 3 will be common, so that will be z. Since I took a negative sign out here, this negative 6, the negative on the 6 will change and become positive. 3 goes into 6 twice. And you know, if we do this factoring correctly, these two parentheses should always come out to be the same. So they will now become z plus 2. And then taking our 4z and minus 3, that will become our second factor. So like I said, if this seems like, oh, I don't want to do all of this mess, then go ahead and use the quadratic formula. But basically this is what I'm looking for: z plus 2 as my first factor and 4z minus 3 as my second factor. Okay, so using this answer, I can actually go ahead and now factor my left hand side. So this will, remember, z is tangent of x, so you will have tangent of x plus 2 as one factor and 4 times tangent of x minus 3 as my second factor. So you're just replacing the z now with tangent of x. Okay? Alright, then remember, at this point you just take each of your factors, set it equal to 0. So this was all of our scratch work here. Okay, so I'm going to take tangent of x plus 2, set it equal to 0, or 4 times tangent of x minus 3, set that equal to 0. You're trying to get the tangent x function by itself, so start by subtracting 2. These guys cancel out, and we've got tangent of x equals negative 2, or here we're going to add 3, so they cancel out, and then you are left with 4 times tangent of x equals 3. To get the tangent function by itself, we divide both sides by 4, and of course we end up getting tangent of x equals 3/4, right? Okay. So remember, now we use the inverse tan function here. So for this guy, we will have x equals arc tangent of negative 2. And for this guy, we will have x equals arc tangent of 3/4. Alright, so let's see what kind of answers we're looking for here. So once again, just to refresh your memory, remember the range of the arc tangent function goes from negative pi halves to positive pi halves, and that's not including the endpoint, so that's why you have parentheses on the negative and positive pi halves. And then of course the tangent function has a period of pi, so that can help us out. So basically we will end up getting in the general form, our answers would be we would have x equals arctangent of negative 2 plus n pi, and x equals arctangent of 3 pi over 4 plus n pi. Now you do want to make sure that the answers you are getting from arctangent of negative 2 and arctangent of 3 over 4 are going to be within the range of the arctangent function. So just use your calculator, and that's the tangent inverse function. So at negative 2 you are getting approximately, so this guy as a decimal comes out to be approximately negative 1.107, and of course it keeps going. And then for arctangent of 3/4 you are getting approximately 0.644, and again I'm kind of rounding these answers off. So remember, your pi half is basically half of 3.14, so approximately 1.57, both positive and negative. So these guys are approximately negative 1.57 and positive 1.57. So you can see these numbers are going to be well within the range for our arctangent function, so that's why we can keep both the answers. Now let's say for any reason these x equals arctangent of negative 2 or x equals arctangent of 3/4 were going to be outside of the range, then you couldn't include them in your answer. So the decimal approximations are just for us so that we know our answers are good to go. So these are the solutions we are looking at for this example. Okay? Alrighty guys, so this was how we can use the inverse functions to help us solve some of our examples here. And especially because you're not going to get nice clean angle measurements like we did for the previous examples, and that's really the main reason why we're having to use the inverse function, and we cannot just go to our unit circle and find the angles for these examples. Alright, so this example here is talking about how you can actually use the quadratic formula itself, because in this case factoring does not work. So you've got sine squared of x minus 3 times sine of x minus 2 equals 0, and of course they're asking us to find solutions specific to the interval 0 to 2 pi. So they're telling us since this expression cannot be factored, we're going to use the quadratic formula. So remember, for sine squared of x, your coefficient is 1. For the sine x, which is your middle term, your coefficient is negative 3. And then your constant term is negative 2. So the 1 becomes your a, negative 3 is b, negative 2 is c, and then they plug it into your quadratic formula. So that's negative b plus or minus square root of b squared minus 4ac divided by 2a. So they go ahead and simplify that right hand side, and this is what they're coming up with. 3 plus or minus square root of 17 over 2. So if you take the decimal approximation of the right hand side, 3 plus square root of 17 over 2, you are getting approximately 3.5616. And then 3 minus square root of 17 over 2 is giving you approximately negative 0.5616. So since the range of the sine function only goes from negative 1 to 1, we actually cannot use this answer over here. So you will have no solution for this first part of x, sine of x equals 3 plus square root of 17 over 2. So the only answer we are going to be getting is from the second portion, because that was negative 0.5616, which is within the range. So for this part, you will notice we're actually falling back to using the inverse function. So you're doing inverse sine on 3 minus square root of 17 over 2, which is giving you approximately this answer here, negative 0.5963. And since they wanted us to find the answer, specifically in the interval from 0 to 2 pi, we're actually going to fall down to our graph to help us out with that. So we start by graphing our y equals sine of x function, which is of course this curve here. And then we are also looking at, since our decimal approximation was negative 0.5616, they are also graphing this little dotted line, which is your approximately negative 0.5616, and we want to see where our graph is intersecting at that line, negative 0.5616. So these are the 2 points from the interval 0 to 2 pi that we are interested in. So this is your 0, and this one here is going to be your 2 pi, right here, this mark. Okay, so these are the 2 points that we are interested in finding. So what's happening here is this answer that you got, that x equals negative 0.5963. So you can see this number here, where my sine x curve is crossing the x-axis at, is actually right at pi. So if you just draw a vertical line from there, you see this little distance from that vertical line I just drew to this point right here, where my curve crosses the pink dotted line. That little distance that you have here from the vertical line I'm drawing from pi to this point, this little distance here is actually that plus 0.5963. So that's why you have x equals pi plus 0.5963 for this point here, because that's talking about that little distance between pi and when you cross the pink line. For my second point, which is this second point which is crossing the pink line, again with respect to 2 pi, since that is to the left of 2 pi, you need to subtract, and so that's why you are subtracting that little distance of x of negative 0.5963 from your 2 pi to get your x. So that's actually where this idea of this answer that you got, 0.5963, is coming from to help us find these 2 points. So those are going to be your answers, and then of course you can put this in your calculator and find your decimal approximation. So that's coming out to be x equals 3.7379 and x equals 5.6869. So in this case, since we have all these funky looking answers, we don't want to leave them as exact solutions, because your exact solution would be this arc sine of square root of 3 minus square root of 17 over 2. So to avoid that, we're actually writing our answers as decimal approximations. So I know it's a little bit of a, I guess there's just a couple extra steps involved in trying to solve this example, but I'll try and do my best to show you how you can do problem number 10 in this case. So we are given sine squared of x plus 2 sine x minus 1 equals 0, and again we're doing this specifically in the interval from 0 to 2 pi. So let's take a look at it. Okay, so just to kind of show you this in terms of just as a quadratic equation, so if you think of your sine x as being our variable z, then you've got basically z squared plus 2z minus 1 equals 0. Right, so we're just replacing these guys with z squared and z. Now you're looking for two numbers that multiply to give you -1 but add up to give you 2. Now, if you're going to multiply two numbers to get -1, that basically means one number has to be -1, the other has to be +1, right? But when I add -1 with +1, I get 0. I do not get 2. So that's why you cannot factor this. And since we cannot factor this, we are going to use the quadratic formula here. So again, my leading coefficient here is 1, which is my A value. My middle term is +2, which is the B value. And my constant term is -1, which is the C value. So we're going to put this in the quadratic formula. And since we're actually doing the quadratic formula on the sine function, it's going to be sine of x equals -b plus or minus b squared minus 4ac divided by 2a. So that's b is 2 plus or minus 2 squared minus 4 times 1 times -1 over 2 times 1, right? We're just plugging in our a, b, and c values. So this will give you -2 plus or minus, and we've got 2 squared, which will be 4. And then we are multiplying -4, +1, and -1. So the two negatives will become positive. And then 4 times 1, of course, is just 4. You get 2 on the denominator. Let's clean this up. So you have -2 plus or minus square root of 8 divided by 2. You can't simplify that square root of 8 and square root of 8, and of course you can write 8 as 4 times 2, so square root of 4 will be 2, and then that last 2 will continue to stay inside. So we end up getting 2 square root of 2, and again the whole thing is divided by 2. Clean this up. So I'll take this 2 and divide it into the -2 plus or minus, and I'll also divide it into 2 square root of 2, and it will be easier to see that how these guys cancel out and these guys cancel out, giving us -1 from this first term, and then plus or minus square root of 2 from the second term. So this is going to be what our sine of x function is going to equal. Okay, so just using the quadratic formula and taking the coefficients from our given problem, we were able to find what our sine of x function is going to be. Now let's see what kind of decimal approximations we are looking at. So once you do that, now we're going to take sine of x equals -1 plus square root of 2, or sine of x equals -1 minus square root of 2. So if you put these guys in your calculator, you should get, for -1 plus square root of 2, this guy is coming out to be approximately 0.4142. And for this guy, it's coming out to be approximately -2.4142. So again, remember guys, the range of the sine function only goes from -1 to +1, which means we have no solutions. I'm trying to see how I want to write this. So for this guy here, we have no solution because it is outside the range. Of the sine function. Okay, so since -2 of course is well beyond this range of -1 to 1, we're not even going to bother with this answer. So you're only looking at the left-hand side where we had sine of x equals -1 plus square root of 2. Okay, so we are going to come back down here. And remember here you are going to use your inverse function. So you're going to rewrite, I guess I'm going to make a line here. You're going to use the arc sine or the inverse sine function and get this. Now let's see approximately what does this answer come out to be. So this is sine inverse of -1 plus square root of 2. And this is coming out to be approximately 0.4271. So we're rounding these to 4 decimal places. Okay, so if that's the idea, where you are getting inverse sine to be 0.4271, remember this is your angle. We are saying x is equal to 0.4271, so that tells me this is actually going to be a quadrant 1 angle, right? Because that's a positive angle and it's smaller in value than pi half. So this is between 0 and pi half. So of course that's going to fall into quadrant 1. So since you have positive sign values in quadrant 1 and quadrant 2, you can also find an angle using this number for quadrant 2 also. So let's see what our quadrant 2 angle would be, because again remember sine is positive in both of these quadrants. So we are looking at, to find the quadrant 2 angle, so this is in quadrant 1. Now for the quadrant 2 angle, we can find that by using pi minus 0.4271, because of course the quadrant 2 angle here is pi, so that's what we're using. So pi minus 0.4271, and this angle again will approximately come out to be 2.7145. And we're only looking for angles to go in the interval from 0 to 2 pi. Of course, quadrant 3 and quadrant 4, your sign will be negative. So, of course, we're not interested in finding angles for negative sign values. So, your two answers here is going to be x equals 0.4271 and x equals, well, I guess we should actually say approximately equal to 2.7145. Okay. So again, like I was saying before, start by using your coefficients. Use the quadratic formula to find your sine x values. You're going to come up with 2 because of that positive and negative sign. So we cannot use sine of x equals -1 minus square root of 2 because that falls outside the range of the sine function. So he is gone. So we are only using this side here, and we're using sine of x equals 0.4142. So using the inverse sine function, then you can come up with x equals arc sine of -1 plus square root of 2, which approximately as a decimal answer is 0.4271, which falls into quadrant 1. Now since we know that sine is also positive in quadrant 2, we can find a second angle by doing pi minus this 0.4271, and that's how you came up with 2.7145, and those were our two answers for this example. Okay, so this was number 10. All right, So this brings us to our very last example, and I know this section is a little bit longer, but we're almost at the end here, guys. So this one is talking about an application, finding the surface area of a honeycomb cell. So we are given the equation for the surface area, which is a capital S, and since its area is going to be in square inches, and that is capital S equals 6 times HS, which is little s, plus 1.5 s squared, multiplied by the quantity square root of 3 minus cosine of theta over sine of theta. And they're telling us theta is going to be between 0 and 90 degrees, not including 0, but including the 90-degree angle. So they're telling us what is basically the height of the honeycomb cell, which is going to be 2.4 inches. And they're telling us S, which is actually the measurement of the one side of that honeycomb, which comes out to be 0.75 inches. And then they're telling you how they're looking at that angle theta here in the figure below. They just want to know what should be the value of theta that you get the minimum surface area for this honeycomb cell. So this is actually kind of looking at the maximum and minimum values that we had again seen in college algebra and using that same concept here. So you will see we go ahead and put these values for H and S in our equation, and then we basically have to figure out what the value of theta is going to be. So for the value of theta, you are actually having to use a graphing calculator to do this. Make sure your calculator is in the degree mode. They're saying use the minimum feature in your graphing utility to basically come up with that approximate value for theta. And so you can see they have that little star showing you where the minimum value of the function falls, and that is coming out to be approximately 54.7356 degrees. And so in this case, we are actually having to fall onto the graphing calculator to come up with this answer. So, obviously, since it's a graphing based question, you're not going to have this on your exam since we're not asking you guys to use a graphing calculator in this class. But I just kind of wanted to show you what kind of applications could be coming out of these sort of functions where you have both sine and cosine function in there, and how you would be able to come up with it. Now, of course, in the calculus course, you would actually be able to come up with the exact area value, in this case, the exact angle, which would come out to be the inverse cosine function, arc cosine of 1 over square root of 3. So your textbook actually had the same example they wanted us to use, where they're giving you a different height for the honeycomb. Your side is still the same, 0.75. So basically they just changed the height and kept the measurement of the side the same, and they wanted to know what this comes out to be. So for me to be able to show you how this comes out to be, I'm actually going to have to try something a little bit different here. So let me see if I can show you this, because I actually have a printed copy of this. Okay, so I've actually pulled this up from the website of the author of our textbook. So this is where they're using that height of 3.2 inches, as you can see, and of course the cell side, which is still 0.75. So when we put this in our equation formula, you have 6 times HS, so that's 6 times 3.2 times 0.75 plus 1.5 times 0.75 squared. So you will see that comes out to be S equals 14.4 plus 0.84375, and then we're multiplying it by this parentheses, square root of 3 minus cosine of theta over sine of theta. And then you can see again using a graphing calculator, by putting this equation in, our minimum value comes out to be at 54.7356 54.7356. So that would be the answer for example 4 in here. Now let me see if I can go back to where I was. So 54.7356 is what you actually end up getting for that guy, and I don't want you
The
to
surface
see it
area.
because there's a video actually. So this is the website called larsonprecalculus.com. You can go through those and look at some of these solutions that they have. So if that helps you, you can definitely look at it, but I wanted to go back to our handout. So I wanted you to show that this is 54.7356, and even though we changed the height of our cell here, we got a height of 3.2, we still actually ended up getting theta to be approximately the same answer, 54.7356. So you don't really see a difference between the answer we got from our example 11 to problem number 11. We still ended up getting the same approximate answer. So that's going to be the angle, which will give us the minimum surface area for this honeycomb cell. So I just kind of wanted to show you that even though we will not be doing that example for our exams, I just wanted you to have an idea for this. All right, guys, so like I said, I know this is a little bit of a longer section, but let's try and get through these examples. So we'll talk about this at our next lecture. If you have any questions, let me know, and I will see you guys in class. All right, have a wonderful day, and be careful, guys. I will see you next time. All right, bye-bye.